Hey everybody, welcome to Data Umbrella's webinar. I'm going to do a quick introduction and then I will open up the presentation. Nidhin will be doing the presentation, the tutorial. And if you have any questions, just ask in the chat. We will sort of, Nidhin will answer the questions as it's a good point to answer the question. This is being recorded and will be available on our YouTube. A little bit about Data Umbrella. We are a community for underrepresented persons in data science, and we are a nonprofit organization. This is our team for Data Umbrella. We have a great team of organizers in a lot of different countries. And I am a statistician data scientist, and you can find me at Reshma S on Twitter, LinkedIn, and GitHub. We have a code of conduct. We're dedicated to providing harassment-free experience for everyone. Please keep that in mind with the chat as well. Thank you. There are various ways that you can support us. The first and foremost is to follow our code of conduct. We also have a Discord server where you can join to ask and answer questions and share events, job postings, and such. Another way that you can support Data Umbrella is to donate to our nonprofit. We are on Open Collective as Data Umbrella. And if you work for a company, a lot of the companies use Benevity. And what Benevity does is it does a company match. So if you donate $50, your company will match $50. We have a YouTube channel with all of our recordings for the past 2 years. And that's youtube.com/c/Data Umbrella. Check it out. And this will be recorded and posted there. And we have a bunch of playlists such as career advice, data visualization, data science beginners. We do a lot of events on contributing to open source as well. And we've done a bunch of series on scikit-learn, PyMC as well, and a few on NumPy. We also have a monthly newsletter. We only email you once a month, so we promise not to spam you. It is dataumbrella.substack.com. So if you want to sign up for it. Our website has a lot of resources on conferences. We're working on an event board that's coming soon. We have guides to inclusive language and allyship, accessibility and responsibility. We encourage you to check them out and to learn more about how our community functions. We are on all social media platforms as Data Umbrella. Twitter and LinkedIn is where we are the most active. If you want to learn about upcoming events, Meetup is the place to go. That is the first place that we share our events. And we as well have a blog, blog.dataumbrella.org. And there's a lot of fun stuff there. I check that out as well. And I've mentioned YouTube and the newsletter before. This is actually not applicable, I think, to Zoom. I don't think we have transcript option. So I'm going to quickly pass over this one. We have timestamps for all of our events. And so I'll share this issue in the chat, but if you're interested in doing timestamps, I think we have 5 videos left. We're actually in a good place for the videos, and it helps viewers to get to the part of the video that they're most interested in. And I'll share the link to the issue in the chat once I've finished my introduction. We have a couple of our August events. We're going to do an introduction to React on August 16th, and we are doing software engineering for probabilistic programming on August 23rd. So if that interests you, we encourage you to watch out for our Meetup group. Those events will be posted soon. Today's talk is serving Pytorch models in production, and it is with Nidhin Pattaniyil. Nidhin is a machine learning engineer in Walmart Search, and you can find him on LinkedIn and GitHub as well. So with that, I am going to hand it over to Nidhin and stop my screen share.
Thanks, Reshma, for the introduction. Hi, everyone. Thanks for spending your time on the weekend for my presentation. So let me start sharing my screen. So today, let's talk about serving a BERT model in Pytorch. in production. So today's agenda is, I'll briefly talk about how Walmart search uses machine learning. We'll review some deep learning concepts. And then there'll be a small, like 2 notebooks that we might go over. Then we'll talk about how do you take this, trained model, what are some techniques we can use to optimize the model for production. Then we'll talk about how to package this model using Facebook's PyTorchServe and how to actually serve this model. And Rishma already introduced me, so I'll just skip this slide. So, how does Walmart search use machine learning? So in a search system, there are different areas where machine learning can be used. One is like spell check, if a user mistypes something, or another thing is, type ahead, helping users complete their query so they can find their items, formulate their queries much faster. If a user couldn't express their intent correctly, kind of helping show them queries that better match their intent. Trying to parse item understanding, trying to do query understanding. Someone types a query, how to extract the token that expresses product, gender, age, or other attributes that a search system might care about. And obviously ranking the results in a personalized manner for the user. So these are just some areas where machine learning can be used in a search system. So today I want to mainly focus on query and item understanding. So let's take a query like Nike men's shoes. When a user enters this query, like as a search system, you probably want to extract that, hey, the brand is Nike, the gender is men, the product type is, there might be different types of shoes, athletic shoes, casual, dress shoes. So you want to kind of extract that this is the user is probably looking for athletic shoes. And then on the item side, hopefully some of these attributes will be provided by the vendor or when the item is onboarded to the system, but sometimes these attributes may not be properly added to the system. So today's model that we'll be focusing on is building a product type classifier. So given like a text, can we extract the product type? Can we extract the best product type? So I mentioned like there's going to be a focus on production in this session. So just a bit of background. So in Walmart search until like last year or so, we were mainly like a TensorFlow shop. So we had models written in TensorFlow, and we like most of our backends were in Java. So we were using like the Java native interface for serving these models. But just like everyone else, or we wanted to start exploring serving larger models. And the PyTorch ecosystem is a little bit more active. Some of the newer models or some of the ecosystem is better maintained there. So how do we change our runtime stack to support serving models with PyTorch, Onyx? How do we support serving large models like BERT? And since this is a production system and it's customer facing, like our maximum threshold for latency was under 40 milliseconds, and that's like the higher end. So that was the section, just briefly talking about Walmart search, the motivation for why we started exploring this project. And the end goal for today is just to show how you can take a product type classifier and some of the steps in optimizing it and serving it. So for today's session, we won't really be focusing too much on the training aspect, but if you are interested in what an e-commerce data set looks like, Amazon and UC Berkeley has a really nice e-commerce data set where they have product metadata and pretty high quality catalog images. So the model that we are going to explore today, it's already trained, but the training data that I used was from this data set. So we have, for an item metadata, like for the items, the subset of items from Amazon's catalog, you have the item title, the product type, brand, and other information. So we'll look at the training code a little bit later, but basically the objective of the model that was trained was, given the item title, can you predict the product type? So, after the model is trained, we will package it with Facebook's PyTorchServe, and there'll be an endpoint that you can basically hit. So in this case, we're querying the product type classifier with the query herbal tea, and we see the most probable classes. So Reshma shared this link in Zoom chat. Let me just share it again. So here is a custom Jupyter Hub instance that has all the dependencies already installed, so you can follow along if you desire. Cool. So let me just yeah. So maybe before I go in the next section, like if there are any questions on the previous slides, or if you're facing issues, if you couldn't open the Jupyter Hub link, or feel free to ask. Let me just check in Zoom chat to see if I missed anything. Cool. I'm going to just maybe continue along a little bit. So definitely at this moment, please try to open this link, and because it can take like 3 to 5 minutes for the server to start up for you. I'm going to just continue along a little bit, and then the next section we'll actually start looking at some of these notebooks. So let me So I mentioned we are going to look into like a product type classifier, which is basically a multi-class NLP problem, right? So what is some models that we can use to solve this problem? So a simple model, and which is what we have been using in production before, is you have an input layer where you're basically taking the input, maybe break it down by white space, right? So now you have your tokens. You feed it to an embedding layer. The embedding, you can initialize it with existing embeddings from Word to Vec or Glove or whatever embeddings, or you can learn it completely from scratch, assuming you have enough data. And after you have the embeddings, you feed it to like a recurrent layer, whether it's LSTMs, GRU, or whatnot. You can have multiple LSTMs, multiple GRUs, and if you kind of want to capture context a little bit, you might introduce bidirectionality to this. And then in the end, you have like maybe a softmax layer to basically get the top product type, a top class. So this is a common architecture that was used for several NLP problems, for multi-class classification problems. But one of the issues with this type of model is, it doesn't really support out of vocabulary words, right? So since you're tokenizing on white space, if there's a token that is a misspelling, like there's no embedding that comes there. RNNs can be a little bit slower to train because of the recurrence way of the model. And the other thing is, if you add bidirectionality to LSTM, you're kind of learning the context not in an optimized manner, right? You have the embeddings learned from the left side, and then you have the context generated from the right side, and then you're basically concatenating it. So you don't really get pure contextualized embeddings. So, these days, everyone uses BERT. One of the nice things about like a generalized language model like BERT is that it with the kind of a simple model, you can easily change this architecture for solving many use cases, whether it's machine translation, question answering, classification, or whatnot. So there's a lot of beauty in the way the BERT architecture was introduced. Some other things that the BERT model kind of solves is, it doesn't just tokenize on white space, right? So your tokens are not just words, it's subwords. So this kind of partially helps alleviate, the out of vocab words. The other thing is, the way that BERT is trained, you learn pure contextualized embeddings. It's much better than the LSTM approach. And the other beautiful thing about BERT is you can learn it in, you can pre-trained BERT in a semi-supervised manner on a much larger corpus. Yep. So, and I mentioned BERT, but BERT has some hyperparameters like the number of layers, number of hidden layers, and depending on the layers you add. So if you look at BERT Tiny, it has 2 layers. If you look at BERT Medium, it has 8 layers. And on a Stanford sentiment data set, which is basically binary classification, you can go from 83% accuracy for a small model to 89% accuracy on a larger model. So depending on your problem, this accuracy jump might be beneficial, but you're going all the way from 2 layers to 8 layers. So here's an example actually from our production infrastructure. So let's take the query bedding for twin extra large matters. On the left-hand side, you have like the original model that we had, the Bi-LSTM model. You see the top class label is mattress, right? So it's focusing on the last token. But if you look at the query bedding for twin mattress, the core user intent is actually the bedding, right? It's bed sheets. So on the right-hand side, you see like, the BERT model that we trained. So it's able to get the correct product type bed sheets. In general, like going from the Bi-LSTM model to BERT, our F1 score metric on our validation data set like improved from 0.75 to 0.91. So this is a great win for us. And this is one of the reasons why we wanted to see if we can serve and productionize this model. Cool. So this might be a good section to kind of let's just go into Jupyter Hub. Let's kind of just run through some of these notebooks together. And yeah, so let me.
Nidhin, there's one question.
Sure.
It is, I'm not hands-on NLP, but is there a scenario when non-transformer models are used in Walmart in specific or in general when there's so much data available?
Yeah, so that's a great question. So, do you need to use, large models? If you have enough data, the models could be hopefully with enough engagement data or with enough label data. We would hope that maybe the models can learn enough, but as I shared, like as I shared, sorry, in this slide here, like even like a simple query like this, like so this is one of the smaller, longer queries that we get. Sometimes users enter really long queries. So for those type of queries, we don't really do very well on, but for shorter queries, with enough engagement data, we really perform well on those. But like for kind of longer term queries, this is something we don't really perform well on. And as you can see from the validation metric of F1 score, there definitely is a benefit in considering exploring these larger models. Yeah, so other question is, what would be the case if anywhere Bi-LSTM? Yes, so I think maybe the question got cut off, but I think like, so like originally we were using Bi-LSTMs and GRUs, and we were using TensorFlow. So TensorFlow and had pretty good Java support, and so it was just easier for us to onboard models. But with kind of newer people joining our team and they're more comfortable with Pytorch and people wanting to use transformers, that's one of the other reasons why we decided to use Pytorch. Yeah, so Sangam, that's a good question. Why would you prefer, smaller models like Bi-LSTMs versus transformer models? So one thing that we're going in the presentation, I hope we can focus on is like latency. So as you'll see at the inference time for running some of these models, it's going to be a really long time. And in a case for like an e-commerce application, ideally you would want the inference time to be like in milliseconds. And especially if you think about in the search stack, understanding the intent of a query is kind of the first layer in the entire user journey. So, if you take like 1 second to, get the most accurate intent, but then, retrieving the items and all the other pieces that happen, like it'll just be delayed, and a user might not wait like 2 seconds for you to get the ideal results. But yeah, that's a great question. Let's take a look at this in one of the future notebooks that we'll have. So I hope everyone was able to see. I see like most of the people's server started. So let's just go to Jupyter Hub. So let me just close all these things. Feel free to run these notebooks. So in the home directory, you should see a folder called workshop. There should be a folder called Pytorch serving workshop. This is a Git repo. So in the slides, if you have seen a bit.ly link, it'll show you the full link to the repo. I can share the repo link afterwards also. So let's go into notebooks. And let me just shut down all my kernels. So, we won't have time today to look into the training code, but if you are interested in, seeing the steps I use to prepare the data set and to train a model, feel free to look at notebook 00 and 01. But for this section, let's just look at reviewing how to take, a model that either you trained or your coworkers trained, and let's look into what the inference API might look like. So I'm just going to duplicate this notebook for myself. Yes, let me just clear all the outputs. So as many people, a lot of people use Hugging Face's transformers library. It makes things very easy to use. So this is something also we use internally. So let's take this Distilled-BERT model that was trained on this data set. So if you're using the Hugging Face API and not necessarily pure Pytorch, Hugging Face makes it easy to load a model. So they have a class auto model. Hey, David, so I just saw your question. Do you see, like in the home directory, if you click on it, is it completely empty, or let's see how to control that. Let me just quickly look at this thing. It may take some time to load, but it should be there. So if you, let me just, so maybe David, I don't see your GitHub username here, but yeah, maybe I'll just revisit the chat like after this. Okay, yes, yeah. So under workshop and Pytorch serving workshop, there should be another folder called notebooks. And you should hopefully see. Okay, yep. And then once you click on the notebook, hopefully it should open. Oh, okay. So maybe after this section, David, I could take a look. But if you just want to follow, maybe I'll also share the link to. So this is the link to the repo. So, but yeah, definitely let's connect to see if we can fix this issue later. Yeah. So if you're using Hugging Face's transformer library, and if you're, since this is a classification task, Hugging Face has this nice API to kind of train and load a model. If we print the model, we see this is a BERT model, but a Distilled-BERT model. We'll cover distillation a little bit later. And we see that in this model, we have like 6 transformer blocks. So in the Amazon dataset, we have a lot more labels, but here I only chose like the top 30 classes or top 30 product types. So the model that we'll explore can, given a input sentence, classify it to one of these product types. So yep, so this is just a mapping from the strings to a numeric label. So now let's take a look at the tokenizer. So as we mentioned in the slides, one of the things that BERT introduced was a tokenizer that was just not on white space. It's a subword tokenizer. So let's take a look at how, like, feel free to play with some of these queries here. So let's see how the tokenizer changes. So do I have a slide? Yep. So here, we're given this query. So this query is, cheap professional men's shoes. These are the tokens that this query got broken down to. So we see like 1, 2, 3, 4. So there are like 4 tokens, but there's a subword that it was broken down into. So there's actually 5 tokens that the tokenizer broke down to. And we see all these zeros here because I believe the max length is like it's like 256 or something. So that's why there are all these other tokens here. And how do you feed the output of the tokenizer? So which has these input IDs, which are the numeric IDs for the tokens. This is how you might just feed it to the model. And since we have about 30 classes, so this is why there's 30 entries here. And now you can just use regular Pytorch to get the softmax, apply the softmax on this, get the top label, and then map it back to your classes. So for this query here, which was professional men's shoes, the top label was shoes. Let's see. So if you're interested in how you might be able to use the batch API, there's some code here, but I just wanted to show how you can take a trained model and run a single input inference. So yeah, let's see, what is the next? I wanted to, okay, so now let me just shut down this kernel, and let's actually look at the probably more important one about the timing thing. Let me again just duplicate this notebook. Just clear all the output. So as you saw, like in the BERT model, like you can, if you add more attention heads, you can improve the accuracy. But let's see what is the cost that we pay in inference time for this. So let me just, so we're going to explore 3 models. So we're going to explore BERT large, BERT base, and Distilled-BERT. So let's look at how much time it takes to run inference. Sorry, the Jupyter Hub instance that you guys have, that you all have, doesn't have a GPU. So like this code block might not be useful in this session, but if you look at the output in the notebook, it was run on a GPU. So, but for today's session, we'll just be looking at CPU timing. So feel free to just run this, queue it up in the background. So I'll just run this. So while this is running, let me maybe just open the output from this notebook. So when I ran this, so for BERT large, for BERT large model, on a CPU, it took about 734 milliseconds for one iteration. So on a GPU, when I ran it, it took about 278 milliseconds. For BERT base, so we went from 734 to 217 milliseconds. On a GPU, this time we went from 278 milliseconds to 43 milliseconds. So this is kind of getting closer to what is acceptable for us in production, but it's still a bit higher. So let's look at this Distilled-BERT model. So we see like on a GPU, it's 26 milliseconds. On a CPU, it's 112 milliseconds. So this is a little bit higher, but it's still, you see like a Distilled-BERT model, we went from it's 112 milliseconds all the way compared to 734 milliseconds. So, you can always add attention heads in your model and you can always get better accuracy, but the larger model do pay a penalty in inference costs. So if you're serving it in production in real time, this is something you might want to consider. So yeah, so what is an acceptable range for production? So in our case, like since we are customer facing, every millisecond actually counts. So I think I shared in the slide the maximum 99.99, like P99, that might be acceptable for us is like 40 milliseconds. But that's like really on the higher end, because since this model is like very upfront in our model stack, and this information is used by other models, yeah, even lower is better. Yeah. So cool. These were the two notebooks I wanted to kind of go over. Feel free to explore this notebook later in Git, but just in the interest of time, I'm just going to go forward. So let's see.
Nidhin, I don't know if you answered the question, but somebody asked, what's the acceptable range in production in terms of less than 40 milliseconds, or did you answer it already?
Yeah, so that's what I meant to say. Like, so for us, for this model, it's under 40 milliseconds, but that's like a very, very generous thing. Like, if we want it to be under 20 milliseconds for this model, but it's acceptable for 40 milliseconds if that was the highest we can do. But you'll see that we are able to do much better. Cool. So we saw how to take a trained model, do inference on a single input. We saw the timing it takes for running this, and on a Distilled-BERT model running on a GPU, we're getting 26 milliseconds, so which might be acceptable. So let me continue with the slides. So Ritesh, you asked a great question about, can you cache models outputs? So that's a great question. And actually, that's what we are also doing in production for, as you can imagine, like if you have the same model and the same query, you can easily cache the prediction output and you use it. But one of the reasons why the team embarked on this project was we were not really doing well, like on really long queries or infrequent queries. And that's also because we didn't really have a lot of engagement data based on those queries. So when this model was launched, it was actually aimed or targeted for queries where we're not getting a lot of engagement data. So it's kind of infrequent queries. But yes, definitely, it does make sense to always cache your top frequently asked queries, so there's less load on the actual model serving. So several techniques for optimizing a model. The first technique is quantization. So, when we trained our model and when most people train their models, they usually use 32-bit precision. But, for inference, do you really need such a high precision? Now, most of the time we can convey the same information with maybe 16 bits or even 8-bit ints. And, going from 32-bit to 16-bit, you're reducing the storage needs by half, and going to int at 8-bit precision instead of 32-bit precision, you're reducing the storage by a quarter. And not only are you reducing the storage, but you're also reducing sometimes the computational needs. So definitely on a CPU and even on some GPUs, int8 computation is much faster than 32-bit. So there is some penalty for using this lower bit precision. So if you look at the histogram on the top, so from Amax and negative Amax, so here you have a floating bit range, But now if you compress it down to -120 to 127, and only storing the data from the histogram as these int bins, we see like we're still capturing the shape of the histogram, but there's a lot of data that's kind of lost. But depending on your problem, like a 4x speed in computation with maybe a slight bit loss of precision might be acceptable. So in PyTorch, there are like several different types of quantization. But in all the quantization techniques, you quantize the weights. So a dynamic quantization is the most simplest one to approach. So basically the weights are quantized, the activations are quantized on the fly. And so you're going to have int8 computations for the weights, which have already been quantized. Activations are quantized on the fly. So you have int8 computation. And this is enough for most people's use case. You definitely will see it speed up. And this is how you might use it in PyTorch. So there's a submodule in Torch called quantization. There's a method called quantize_dynamic. You pass the model instance. You tell it which layers in the model you want to quantize and what level of precision you're interested in quantizing. There's two other techniques. So like, instead of like blindly mapping from 32 bits to 8 bits, you can like provide like a calibration data. And PyTorch would then use this calibration data to kind of find a better mapping instead of just just blindly mapping the weights. So that's what static quantization is. And then if you know that you're going to quantize your model, you can tell your model while training to also optimize for the quantized error loss. So quantization aware training is a little bit on the advanced technique, but if you know you're going to need quantization, this will give you the best accuracy results. And here is the results of quantization applied for 3 models. Today, since we're talking about BERT, let's just look at the first row for BERT. So for 32-bit floating points, we have a 90% accuracy on the Stanford sentiment analysis dataset. After converting it to 8-bit, the accuracy dropped by 0.5%. So we are 89.5%. But if you look at the speed up, you're able to get, like in this case, about a 2x speed up. So from 581 to 330 milliseconds. So for a very small drop in accuracy, 1.8x speed up is pretty great. So the other technique that sometimes people apply is distillation. So if you remember in the notebook, we looked at three models: a BERT large, BERT base, and a Distilled-BERT. So what is distillation? So large models like BERT have really have a great knowledge capacity to learn a lot more information. But do you need it all for your problem? You might have a smaller model like a Bi-LSTM. Like, what if you could teach your smaller model? What if you could train your smaller model to kind of learn from the teacher model? So in this case, if you look, we have a much larger model. It has many layers. You get this model's already trained. It has gotten a certain accuracy. Now you have a smaller model that you're going to train. Now for this model, not only are you going to train it on the data, you're also going to train it on the loss that you're getting from the teacher model. So you're basically trying to tell the smaller model to basically learn from the teacher model's loss. So let's actually see the result of this in practice. So in this table here, the teacher model is the BERT large. So on this data set, the Stanford sentiment data set, it has a 94.9% accuracy. And the student model, before being trained, had an 86.7% accuracy when it was just trained on the data set itself. But if you do this distillation process, it was able to increase its accuracy to 90.7. So just by this distillation process, you were able to increase the accuracy of the model compared to if the model was trained by itself. And the other final technique that might be useful in optimizing the model is like script mode. So one of the reasons why Pytorch became a very popular deep learning library compared to TensorFlow is that Pytorch runs by default in eager execution mode. So what that means is, when you're writing a model, you get immediate feedback from the operations of your layers, and which in turn provides great debugging support. And also you can use any libraries in Python, but this kind of flexibility makes it tied to the Python runtime. So in script mode, what Pytorch does is, it compiles the execution graph, like it creates an execution graph. So you lose kind of the interactability that you might have in eager mode, but you really benefit from the speed up from having like this compiled graph already. And the other benefit is, you're not necessarily tied to just Python. If you want to serve it in Java, if you want to serve it in C++, or if you want to serve it on mobile, with a script mode model, you'll be able to do that. It definitely doesn't support everything that the Python eager execution model does, but for most people, this might be sufficient. So how do you compile a model to script mode? So Facebook has this project, TorchScript. If you use their just-in-time compiler, there's basically two modes to it, but basically you can use tracing to convert your model to this optimized model. So let me just show you how you might use this. So let's say we have a simple model like this. You can just call torch.jit.script. So this torch.jit.script.trace, but we're using script because there's like a if-else loop inside the forward function of the model. In the future, like Pytorch might combine these two different optimization modes, but in this case, the APIs are basically the same. So let's look into how much improvement we got from just this compiling of the model. So on the top row, we have the original model running in eager execution mode. On the CPU, it was taking about 1.3 seconds. After running the just-in-time compilation to compile it to script mode, we got a 42% decrease in the time it was taking. On a GPU, it was a little bit smaller. It was only 21%. But this is a simple optimization technique that, just by running this, that you're getting. Yeah, so maybe I'll just, before going to the notebooks, let me just look at the question. Okay, so, okay, let's see, David, you had a question. Is there a difference between script mode versus production mode? Yep, so I hope this, I kind of skipped some of the details in this thing. So like, there's two ways to go from eager mode to script mode. By default, eager mode is what normally when you spin up a notebook and you're training your model, it normally runs in eager mode. Script mode is really meant just only for inference. You can't really train a model in script mode. But because of that, the execution graph is kind of optimized. And there are two ways to kind of go to script mode. So sorry, the names are a little bit confusing. So like the script mode and then tracing and scripting. But yeah, so to go to script mode, you need to use the just-in-time compiler, and there are two APIs to do it. But let's just assume like it basically does the same thing, whether it's in trace mode or script mode. In the end, you're going to get a optimized graph. So let's look into two notebooks that we have. Oh, actually, just one notebook, this notebook 3, optimizing the model. me just close all my notebooks. Shut down this. And let's look into optimizing the model. Yeah, so let me just duplicate this notebook. Sorry, there was a lot of information shared in the previous slide, but I hope in this notebook to show that it's luckily the APIs are pretty clean and it's pretty easy to use. So again, we're just going to import the model. So this code is similar to what we used previously for loading the model, and then we're going to load the tokenizer. And let's load the data set that we're going to use. So Hugging Face has this nice library called dataset, which kind of standardizes, operations on your data sets. So I'm just going to load this data set that I saved. So in our data set, we have a test split, train split, validation split, and we have brand, item ID, and item name. So let me just so here we have our data set. We're just applying our tokenizer on this data set. And since we are running on a CPU, instead of running on the full data set, I'm just going to run it on like 20 rows. So I have a simple method that I basically just put in a separate file to basically run inference on run inference. So we see it took about 7 seconds for running about for 20 samples. So let's look into one of the techniques that we covered, quantization. So as we saw before, Torch has this nice submodule quantization. They have a function that called quantize_dynamic, where you pass the model, you pass the layers you want to quantize, and the return type. So here we're going to go all the way for 8-bit precision, all the way from 32-bit to 8-bit. So you'll see, like, for the linear layers, it's now called dynamic quantized linear layers. But other than that, if you look at the model architecture, it looks about the same. So we see that we didn't quite get, like from 32 bits to 8 bits, getting like the 4x drop, but we're only quantizing the linear layers. So, but we still see like a drop of half in the storage requirements. So let's see. I have some scripts that basically just run the timing, but let's see. I think we have enough time, so let me just run through these cells. Again, since these cells inside this environment, we don't have a GPU, so the output of these cells are not really that meaningful. So this again is just running the 32-bit model. So we see about 7 seconds for the 20 samples that we have. And if you run it on a single sample, it's about like 570 milliseconds. If you look at the quantized model, it can take some time. Oh, here it's this run is still showing it. Okay, so here it was 7.9 seconds. Here it's 7.4 seconds. So not really too much drop decrease here. But in general, quantization does have some speed up benefits. So while this is running, to 531. So here in this run, the drop is maybe not significant. So here in the previous run, when I did this, this is on the full data set, not the subset of 20 that we're running. So it was for one sample, I was getting 116 milliseconds. And sorry, the CPU environment that we are using for this is only like 2 cores. When I ran this, it was running on an 8-core CPU. So there is this could explain some of the drop. So yeah, so for this Distilled-BERT model, we were getting 116 milliseconds on a CPU. The 8-bit quantization, we were able to reduce it to 83 milliseconds. On a GPU model for this 32-bit, we were already getting 17 milliseconds. One thing to keep in mind is, like, especially if you're using a CPU, is like some of these like OpenMP threads, like this kind of controls the parallelism and some of these operations. So this could determine the timing a bit. So we covered quantization, at least from this table. I hope you can see that definitely there is some improvement for quantization. And here, like, this is like a third level precision. So, accuracy might not be the best metric sometimes, but you see we're about keeping the same results. So the other technique that is available is TorchScript, right? So if we have our model, it's running in eager execution mode, and we want to run it in this optimized graph mode or script mode. So if you're using Hugging Face has this like flag called TorchScript equals true. And this is more like an internal thing, like in Hugging Face, because some of the weights and layers are kind of attached together. So this is just some internal flag for Hugging Face to kind of decouple it. So if you're interested, you can look at this doc or this blurb here. So I'm just going to reload the model and tokenizer with this TorchScript flag. This code is basically the same, except the tokenizer and model is loaded with this flag where it just basically decouples some of the layers inside the model. So here's the same input that we got before. And here we're calling the just-in-time compilation and the trace method inside the JIT module. So basically, you just pass in the model, and then you pass it a sample input, and then Pytorch will look at the execution graph that is created for this input, and then basically try to create an optimized version of the graph. So you can combine these optimization techniques, right? You can put it in script mode. You can quantize the model too. So this is just some code for that. I'm just going to maybe go quickly to like some timing information that I had when I ran this. So let me just see if this is the final block. Yep. So when I did this run a bit in the past, so this was the timing information I got. So again, the 32-bit original model, about 130 milliseconds. Tracing dropped it a little bit, like 6 milliseconds, but it wasn't significant. On a GPU, we went from 22 milliseconds to 18 milliseconds. And then quantized and tracing on a CPU, we went down to 90 milliseconds. So if we started from 130 milliseconds we're able to go all the way to 90 milliseconds on the CPU. There are some other techniques that can be applied, but on this setup, this is what we get. So before we go to the next notebook, we want to save the model. So you have your tokenizer dot saving the model. Maybe you might save some config about what is the how many labels you had, the string of the labels. So you're just going to create a JSON file that has, like your internal model name, whether to for the tokenizer, whether to lowercase, and some stuff that might be needed for your model. So this is the purpose of this notebook, just basically showing the different speed up that you might get, and just saving the artifact for our final notebook. Maybe let me take a look at questions before I go to maybe the final section on this. Okay, I don't see any questions. Hopefully some of this, the pacing is okay. If there are any questions, feel free to ask them in chat, or we only have one more section where we're actually going to take this model that we kind of quantized and distilled and traced, and packaging it with Facebook's TorchServe. So that's the final section for this session. So maybe if there are no questions, maybe I will go to this final section. Let me go to presenter mode. So, we explored the latency costs that might be there in the model. We explored how running on running the model with some of these optimization techniques, you're able to shave some of these milliseconds. All of these things do matter. So now let's look into just how you might package the model, whether it's the original model or whether it's one of these optimized models. So there are several options for serving, a PyTorch model. If you're in a Python ecosystem, you might prefer to use pure Python web servers like Flask or Fast API, and they're both great options. You might also explore, model servers like TorchServe, which is what we're going to talk about today. NVIDIA has their model serving solution called Triton, and Google has its TensorFlow serving. We can't use TensorFlow serving since it's a PyTorch model, but you could use NVIDIA's Triton. So why would you use the model server? So the benefits of like TorchServe and in general like a model serving package is that it's kind of optimized or better designed for serving models. You have in a config file, you can easily say like, hey, I want to serve multiple models. You can easily say like, for this model, I wanted to have like 2 CPU cores to have it. I want this model to use a GPU. These model serving libraries have a notion of like multiple versions of the model, so which makes it easier in your company. If you're doing A/B testing, it makes it easier to kind of split traffic to different versions of the model all within one server. It supports batching. So as we know, like if in a GPU, like GPUs are optimized for batch inference. So these model serving frameworks have this setting where you can say like, hey, I always want to run inference when there's 5 records, or I want to, my latency threshold is like 10 milliseconds, wait for like 5 milliseconds, and whatever, if there are more than 1 records, do batch inference on all those records at the same time. So all these settings can be easily configured in a config file. And one reason TorchServe is maybe a better option than like NVIDIA Triton is, I think, as like in the model, there's always like some pre-processing step and some post-processing step that you need to do. And I feel the design that Facebook's TorchServe took is much cleaner than TensorFlow serving and other options. So how do we package the model for TorchServe? So there's a utility from the PyTorch team called Torch Model Archiver. And basically, it's a command, but right now it's just basically going to package it to a zip file with an extension of .mar. But if you see the snippet on the right, it's Torch Model Archiver. You're passing it the name of your model, version. You can put whichever version you want. Serialized file is where you're passing it the path to your your PyTorch bin file. Export path is where the final zip file or MAR file is going to be exported to. If your model needs extra config, you will pass it like in the extra files. And handler is the Python code where, once your model is invoked, if you want to do any pre-processing and post-processing, this is the step that will be done. So on the left-hand side, you can see which arguments were passed to this command. So what is inside a handler code? So it's a little bit small here, but the core thing is, the core thing is this handle method. So the TorchServe has a base handler, which you can extend if you want. They also have like handlers for common use cases like text classification, image classification. So if your use case matches the built-in handlers, you don't need to like even write this much code. You just need to pass in a config file. But in this case, since I kind of want to demystify it, I have like the full code for a custom handler. Again, the main method is this handle method. So this is the method that will be called when a request goes to your model. So you have there's a built-in existing method, pre-process, post-process, and inference. If you want to do like different things for your model, you can override it. Otherwise, it'll just call it by default. But otherwise, by default, the handle method will just call the pre-process method, get the output of that, feed it to the inference method, get the output of that, and then feed it to the post-process method. So inside Walmart, now we started using TorchServe a bit more. So for our teams, we have a custom handler that kind of generalizes for most of our use case. So some of the pre-processing initialization steps, some of the things that we as a production system needs to think about is like metrics. So all these kind of things are taken care of like in our own base handler. So when we as a model developer try to onboard a new model, like there's very minimal code that we need to provide. And in fact, you probably don't even need to provide any code. Actually, before I go to the next slide, here I talked about this extra files section. So if you need to load these files, you can, inside the initialize method, you will get a property that kind of gives the temporary path for those files. So you can load any files that were passed inside that argument. I hope, sorry, I'm hiding a bit of code, but I hope you feel like in general, this, the base, like writing your own handler or using an existing handler, like there are enough hooks for kind of the main use cases that you might have for a model. Again, as I mentioned, like if you are doing like image classification, text classifications, image segmentation, or object detector, like the TorchServe package already has like a handler for these use cases. So, and you just need to provide like a config file. So assuming the input output of those handlers work for your use case, you don't even need to write your own handler. So you ran the Torch model archiver to create this MAR file. How do you actually serve this package? So there's a Python module called TorchServe. You provide this config file, which there's a lot more options, but maybe some options is like, do you want to load all the models? What port should it be listening on? What is the batch size that that you want your models to run inference on? And this is the other parameter, max batch delay of, in this case, it's 2 milliseconds. Oh, sorry, yeah, 2 milliseconds. So it's going to wait for 2 milliseconds for some batch to come. If there's no batch size of 20, it's going to run inference on how many records it has. So, yep. So this is how you would start the server. We'll run through this inside the notebook that we have. So there's some management APIs that are there for this model, for TorchServe, you can hit an endpoint to see all the models. If you hit the endpoint and you give the model name, it'll give you details on the model. And all the models expose a post endpoint. So you hit /predictions and the model name, and you give it a JSON payload, and then your model will be called. So let's look at this final notebook where we'll look into packaging the model and then hitting the endpoint. Yep. So before I go to this, let me answer some questions that were asked. Okay, so David asked, how do you handle a pipeline of models or multiple models feeding into business logic? I assume that Walmart runs multiple models simultaneously, not just A/B testing. Yep, so that's a good question. So we have multiple models, and all these models are they're served over HTTP or gRPC endpoint. So right now there's an orchestrator that basically calls the models in whatever sequence that's needed. So since query understanding, PT classification is kind of one of the first models, or the output of this model is needed in other stacks, it's called first, and then there may be parallel calls to other models that might need that output. So there's an orchestration layer that kind of takes the output of one model and feeds it to other layers. In TorchServe, there is something called a workflow. So if you have a case where you have several models, you can create a workflow where the output of one model goes into another model, and you can create this whole graph. It's a little bit immature, the pipeline. Same thing, like NVIDIA's Triton also has this thing where if you have several models and you need to go to a certain flow, they kind of capture it. But I don't have much experience with NVIDIA's Triton, but from TorchServe, the workflow is a little bit immature right now. Let's see. Ritesh asked the question, in a customer's facing scenarios, how does the batch size help? Isn't it going to be request response by customer? Yep. So yes. So where does how does batch size help? Let's see. Yep. So how does batch size help? So this is something in general, all these model serving frameworks have. So if you're getting if your service is getting thousands of requests per second, and in general, GPUs are great for batching it. I mean, you can run it for one input at a time. So what these model service frameworks do is they can have a queue of requests that are coming in, and depending on whatever threshold that you have, in this case, whether it's 2 milliseconds, if there are certain requests that are coming, it will automatically deal with taking these individual requests, packaging it, sending it to the GPU, unpackaging it, and all that. So for your calling application, it'll still be request response, but for the model service piece, it will deal with creating these mini batches, feeding into the GPU, and then removing from the batch. So this ensures that you're using your GPU efficiently, and you're getting the speed up from serving these requests in a mini batch, and so just doing pure request response. But it's all transparent to the user, to the calling client. Cool. So let's run this final notebook. So let me again just shut down. So the final notebook for today is this packaging notebook. Let me again just duplicate this notebook. So if we ran the previous notebook completely, we would have two models, just the original model and then the traced model. I didn't save the artifact for like quantization or whatnot. So the model that we'll be serving with this is just a traced model. So this is the help instructions for this Torch model archiver. So if you remember, these are the arguments that we can use to package the model. And it again creates like a file with a .mar extension, but it's basically a zip file. So you can unzip it and look at it. Yep. So these are the arguments again. So you need to you can pass whatever version you want, like whether it's 1.0, 2.0, whatever versioning convention you follow for your model. This name is kind of important. This is what, when you hit your endpoint, this is what the model name is going to use for the endpoint name. Again, you pass a folder for where the model is located. Export path is, where would the MAR file be located. Extra files, in our case here, what are the extra files? So we have the tokenizer config, token maps, the vocab from our tokenizer. Yep, so it's just the tokenizer config in our case. Oh, sorry, the model extra file. So yeah, the mapping from class names, the model config.json, and the tokenizer files. So these are the files that we want to be packaged with our model. So I'm just going to run this command. It should create a folder. It's taking some time, that's fine. So this is like the full code for a handler. So again, as we saw in the notebook, like there's a BaseHandler class that, if you want to completely override, you can use. And the core things is the handle method, right? So there are these three methods that you can override if you want, but this is the method that gets called for a request for a mini batch or for a single request response. For inference, so maybe I'll go with the pre-process steps here. So this is the first step that's called. So, whether you are sending the request in just inside the body, or, you're passing it in a certain format, you can iterate across the list of requests that are sent. But, if you have a batch size of 1, it's just going to be a single record. But if you tell TorchServe to support a mini batching, you might have a list of requests. So just parse whatever requests that might be coming, whether you're sending it in the body, sending in some other field. So just parse this request. And then, this is regular Hugging Face, like using the tokenizer, right? You just call tokenizer encode, you're passing whether it's a single token, a single input, or a batch, you're just calling it, you get the input. And then if you're using a GPU, you feed it back to the, pass it back to the GPU, and then you just return it here. So this is, you have tokenized the input. So what happens in inference? So, you just basically pass it to the model, right? And then in the inference step, if you want, you can, apply softmax and get the label, or you can do it in the post-process step. It's basically up to you. In this example here, I'm doing the feeding the model to the softmax, getting the label-friendly names. And so the post-process step here is very minimal, but so yeah, so this is what a full model handler looks like. But again, if you can use the existing handlers, you don't need to write this much code. So the model store again is where so the model store again is where like this zip file / MAR file is created. So this is what I was mentioning, the output of the Torch model archiver. So now we have this zip file / MAR file. So let's call TorchServe to basically serve this say to serve this instance. So I'm just running it in the background. So it may take like maybe 1 or 2 seconds. So let's see if the log files have loaded. Okay, yep. So the TorchServe instance has started. There's several metrics in production that might be useful. Your model log, the metrics log. So if you want to monitor, these are files that you can consume. So yep, so we see that server has started. It has loaded the model successfully. From the config, these are endpoints that we can hit to either manage the model, to get metrics that are parsed from the log files, or this is the endpoint that if you want to hit to make a prediction. So let's hit this endpoint /models. In our case, we only have one model, right? So it returns this TorchServe instance has only loaded one model. So this name PT classifier, this is a name that we passed here, model name as PT classifier. So this is the endpoint name /model name that you hit. We also see it here. Yep. So let's hit this endpoint. So we see in this thing, like this model is going to be served with 4 CPU workers. So there's 4 instances of this model that's loaded. So if you're using a GPU, there's probably only going to be like 1 or 2 GPU workers. But here, since we're doing on CPU, like it's loaded with 4 workers. So let's make a sample request to this model. So with simple curl, we're passing the query, and you can pass whatever information here. So in production, you might maybe want to pass like a request ID or access key or something to kind of track usage. So this is the request that we got for herbal tea. Yep. So let's see. So if you want to use pure Python's requests, so this is how you might make the call. So overall, I think this endpoint is like TorchServe makes it very easy to kind of package a model. Whether it's like the original model, whether it's the traced model, whether it's the quantized model. Those are small things, but at least from a serving piece, TorchServe makes it very easy to serve either of these models. So this is the last notebook that we had here. So let me just look at the questions. Let's see. So I think, Ritesh, I hope I answered the question about batch size and batch inference. Sangam, I see you asked a question. I faced some issues in using HTTP external link for inference. Is there any way to make it work for HTTP? So there might have been an issue when you ran this command. So it does take a couple of seconds to run. Since Jupyter Notebook, since this is like running in a Kubernetes cluster with pods that are like not accessible externally, that's why we're just using like curl to hit localhost. But if you run it inside your own company server, or you'll be able to hit it with the external or internal IP of that. But inside this environment, because it's like running in an internal container, it's not really accessible. Cool. Are there any other questions before we go to some of the very few slides? Cool. Okay. Let's see. Cool. So Ritesh, you asked a question, what are tools to use to monitor the models? Any update for the models? Yep. So so we didn't necessarily look at the log files for let's see, let's go to TorchServe logs. So there's an endpoint which exposes Prometheus metrics if you use that. So otherwise, it kind of says like how long each request took. And I think there's also like one more So if you hit the Prometheus endpoint, let me see if it's shown here. So if you hit this metrics endpoint, like this is a Prometheus endpoint. So if your company uses Prometheus, you can scrape like GPU usage, time it takes to it took for requests, CPU usage and all that. So all these things are exposed to this Prometheus endpoint there. Okay, so Sangam, regarding your question, like only HTTP for local, is there any confusion about HTTPS for external links? Yes, so TorchServe, doesn't take care of any of the SSL or the security aspect of this. So when you serve with TorchServe, it's just like a internal just running on HTTP. So so your internal services that call this would need to talk to it over HTTP. You can't put like an HTTPS layer, but since you should not really be exposing TorchServe directly to the customer or like in a customer facing service, so I think it's fine for internal service to talk to it over HTTP. Yes, so I hope I answered that, but we can continue this a little bit later if there are any questions. So yeah, let's go to the last slides. So I hope you saw in this notebook how you can package the model with Torch Model Archive, and then how you can use TorchServe with your own custom handler to kind of package and serve the model. So what lessons did we learn from Walmart? So sorry, this chart is a little bit slow. I mean, sorry, a little bit low resolution, but the Y column is the time it takes in milliseconds. So these are all under 10 milliseconds. So the architecture of the model is a little bit different than what we covered in today's presentation, but we are able to serve a BERT model in production running on GPUs with under 10 milliseconds. And we also were able to get like 40 milliseconds running on CPU, applying all the techniques that we talked about and some other optimizations. But if GPUs are available in your environment and makes sense financially, it does make sense to use it. So the kind of under 10 milliseconds I mentioned about is with NVIDIA T4. And as someone else mentioned in the Zoom chat, you don't really need to be serving inference requests for every request. For queries that you've already run inference, you can store it in a cache and use that. But yeah, but even with peak traffic, without hitting like a caching stuff, you're able to hit under 10 milliseconds using a GPU. So this was a big win for inside our org, and we have onboarded a lot more models since then. Yep, so this is the last slide I had. If you found this kind of talk interesting or useful, we do have some openings open, so feel free to check the career page or feel free to reach out. Yeah, so this was the last slide I had. I just want to say thank you everyone for spending your weekend on this. I'm open for any questions in the remaining time, or feel free to ask them later also. I'm just going to stop sharing and yeah. Oh, okay. So let's see. I'm just going to monitor question. So Prometheus, so Ritesh asked a question. Prometheus is mostly system monitoring. What about data drifts? Yes, so unfortunately, TorchServe doesn't really monitor, it doesn't really take care of, data drifts or model drift. So these are some things you need to monitor externally. If your company does use like something like Kubeflow serving, like it does have it does have like built-in mechanisms for that, but we don't really use kubeflows, so I can't speak much about that. But yeah, unfortunately, this is stuff that you still need to build externally. Cool. Thanks, everyone. Again, all the material that was covered was again in this repo. I'll just share it again. Yeah, so feel free to look at the notebooks. I hope the example was kind of inspire you for kind of exploring for your own use case how you might serve some of these large models, how you might optimize it. Always open for feedback on this. Feel free to reach out. Yeah. Cool. Yeah, so Reshma and I here will probably be here for maybe another like 20 minutes or so. But feel free to either ask questions or drop if. Yeah.
Nidhin, thank you so much. What I'm going to do is stop the recording now, and then if people want to ask questions, we can do that.
Sure. Yeah, sounds good.